Alright, so for our first problem, Reese and I decided to do chapter 14, Problems Plus, number 1, which is a rectangle with length L and width W is cut into 4 smaller rectangles by 2 lines parallel to the sides. Find the maximum and minimum values of the sum of the squares of the areas of the smaller rectangles. So our first step, we decided to draw out the rectangle with a length L and a smaller length of X, and a length W, or a width W and a smaller width of Y. We separated the rectangle into 4 quadrants, labeled from A1 to A4, and then we found our function, which was fxy is equal to A1 squared plus A2 squared plus A3 squared plus A4 squared. We got all of the areas for that, and that became xy squared plus y times the difference of L minus x squared plus the difference of L minus x times the difference of W minus y squared plus x times the difference of W minus y squared. And that was simplified down to 2x squared plus L squared minus 2LX times 2y squared plus W squared minus 2WY.
Alright, so the next step was, in order to find the maximum or the minimum, we first have to find the critical points. And to do that, we need the derivative, because wherever the derivative of the function is equal to 0, we have a possible critical point. So to do this in a function with 2 variables, we have to first take the derivative relative to x and then take the derivative relative to y. For x, we get this function, which when set equal to 0 gives you this. Now because this will always be a constant, we can just divide it over without having to worry about the fact.
I'm shaking.
Go.
My hands were shaking, so we switched places, and I'm just gonna point for his parts now.
All right. So this fiasco gets to resume. So next we have the partial f, partial y, which is up there. And we set that also equal to 0, which simplifies down for the same reasons to 4, why is my hand shaking?
Just keep going.
To 4x is equal to 2l, which then simplifies down to x equals L over 2. Which means that our critical point is at the point L over 2, comma W over 2. So the next thing we need to do is use the determinants test to find out whether it is a minimum, maximum, or unknown. So to do that, we need the partial f for all of the double partials, yy, xx, and xy. So once we take those, which is shown there, we go over to the determinant test.
So for the determinant test, you have to do the partial xx times the partial yy minus the partial xy squared. And we plugged all of that into this really long thing that I don't really want to read out. But we got to simplify down to 4l squared times w squared. And because the l's and w's can never equal to 0, the determinant d is greater than 0. So now all we need to figure out is if the partial xx is also greater than 0, then we have our minimum. So we got our partial xx and we plugged in our critical point, and we got it simplified down to 2w squared, and because w can never equal 0, we also have our partial xx is greater than 0, which means that our critical point is a minimum.
So we think that it's trying to make it steady, but it's messing up, so it actually makes it way less steady. Because even whenever it was set against a table, it was still shaking. Anyway, that's not relative to our actual equations. I'm gonna get back to that. And, all right, so the next step for us was to find, we know that's the minimum, but we don't have any other critical points. So that we don't have any other critical points. Therefore, the maximum must be somewhere along the boundary. And in order to do that, we have to have a function in which we can take the derivative of to find out what that maximum is. So what we did was we looked at the maximum boundary for y. So what we set up was the function g of y is whenever f of x is 0 and y is just some variable, which means that our function is now a function of L and y because our distance was w minus x, or sorry, L minus x, and when x is 0, that's just equal to L. Therefore, when this simplifies down from our original equation to L squared is multiplied by y squared plus w minus y squared, whenever y is greater than 0 but less than w. We take the derivative of that and set it equal to 0, which means that this, which is the derivative, is equal to 0. Therefore, we divide L squared over, which is a constant, so it can't ever be 0, which means that we now have 2y minus 2 times w minus y is equal to 0, which in turn simplifies down to 4y is equal to 2w. You know what to say.
Okay. He looks like an elf.